Why is the Orion Nebula called a cosmic factory on the assembly line of creation? It can even mass-produce stars and planets. What is even more incredible is it may have already replicated the solar system thousands of times. So in the time ahead, we will dive into its core to see how it creates stars in our galaxy. After watching this, you will realize maybe the universe was not born randomly. It has order, repetition, and might even be replicating us. So how can we find the Orion Nebula? You can see, Orion looks like a hunter raising his sword, with 3 neatly aligned stars on his belt, especially striking, and just below that belt, if the night is dark enough, you might notice, at the position of the sword, there is a small, blurry patch of light hanging beneath it that is not just a cluster of a few stars, that is a real nebula. Its name is the Orion Nebula. Messier 42 or M4 is also known as Messier 42. 42, it is also called Messier 42. 42, it is a bright cloud of gas and dust. It is a cradle of stars. In our galaxy, it is one of the most famous star-forming regions. Human observation, depiction, and recording of this small corner of the Milky Way have continued for generations, far more than anywhere else. The Orion Nebula is located within a massive structure, the Orion Molecular Cloud Complex. It stretches across hundreds of light years. It is a stellar factory, woven together from several famous nebulae. Among them are the Barnard's Loop and the Doc Nebula. They are all like pieces of fabric located between the arms of Orion. 42 is the brightest and most striking part of the entire complex. Even without a telescope, we can see it with the naked eye. That faint, blurry patch of light is right there. It points toward the Orion arm of the Milky Way and our solar system. We just happen to live within this spiral arm. This means that, from a cosmic perspective, the Orion Nebula is not far away. It is not some distant, unfamiliar corner at the other end of the universe. It is right here in our galactic neighborhood. So how far away is it exactly? This is a question scientists have debated for many years. At first, people estimated it to be between 1,500 and 1,800 light-years away. But as observational methods improved, we finally got closer to the answer. The most reliable observations show that the Orion Nebula is about 1,344 light-years away. The margin of error is less than a few light-years. In other words, it is about 7.9 trillion miles from Earth. To put it another way, 1.27 trillion kilometers. This is not just an imagined number. It is based on 2 core astronomical techniques: parallax measurement and radio interferometry. The principle of parallax is very simple. Close one eye, then switch to the other. You will notice that nearby objects seem to move. Astronomers use the 6-month interval of Earth's orbit around the Sun to observe from both ends of the orbit, and can see this kind of shift by measuring the changes in the position of a nebula relative to more distant background stars. They can calculate its true distance. This is a geometric problem on a cosmic scale. It looks simple, but it is extremely difficult to do, and to further improve accuracy, scientists have also used very long baseline interferometry, or VLB for short. This technique combines multiple radio telescopes on Earth to form a virtual super telescope array, simulating a huge and highly sensitive antenna dish. It is especially well suited for observing the Orion Nebula, this vast and diffuse celestial object. In addition, with data support from space telescopes like Gaia, we have now reduced the margin of error in distance measurements to less than 20 light-years on a cosmic scale. That is already quite remarkable, and that is not even the most astonishing part. Surprisingly, the Orion Nebula is not a flat plane. It is not just a simple 2-dimensional bright spot. It is a 3-dimensional region in space. Some of the stars inside are closer to us, while others are much farther away. What you see is not a wall, but an entire misty forest. Some of the molecular clouds on the outskirts. It is even farther away than the T-shaped cluster at the core of the nebula. This means what we see is not a single distance, but rather a thickness of space. The nebula itself is enormous, with a diameter of about 24 light-years, but it only makes up a small part of the entire Orion Molecular Cloud Complex. The whole structure stretches as far as 240 light-years, and the part we can see in visible light is actually just the outermost electric shell. It is like a paper lantern, illuminated by the fire inside. It is both silent and active, which is why M42 has become a benchmark object in astronomy. It is like the Rosetta Stone of the Milky Way. Here, You can see almost every stage of star formation can all be directly observed, from the collapse of cold gas to the process of newborn stars igniting the surrounding gas, from the formation of protoplanetary disks to radiation sculpting matter. These cosmic spectacles are unfolding here simultaneously, and another feature of it is also full of philosophical meaning. The light you see tonight from the Orion Nebula, in fact, it was emitted around the year 681 AD. In other words, what we are seeing right now is Orion as it was 1,300 years ago. Back in that era, dynasties were rising and falling on Earth. Civilizations were changing, while that beam of light was just setting out from the nebula. And if tomorrow a star there exploded as a supernova, we will have to wait another 1,300 years to see it with our own eyes, since what we see is its light from 1,000 years ago. How exactly is this light created? What makes the Orion Nebula shine? The answer lies in an invisible process. Ionization of the Orion Nebula. Like a blazing cosmic flame. Deep crimson and vivid blue, and that strange shade of green, like an oil painting spilled across space. These colors are more than just a visual shock. They are a language, a message written together by chemical elements and spectra. So here's the question. Why is the Orion Nebula so bright? Why does it shine like a beacon in the night sky, while most other molecular clouds remain hidden in darkness, leaving no trace? The answer is ionization, a process driven by Young. The intense processes triggered by massive stars take place at the center of the nebula. There lies the trapezium cluster, a group of stars that have just ignited nuclear fusion. The most powerful among them is called Theta Circumflex 1, or Orion C. Its mass is dozens of times that of the Sun, and it shines thousands of times brighter. It unleashes a flood of ultraviolet radiation, engulfing the surrounding gas, and the Orion Nebula itself is filled with hydrogen, the simplest and most common element in the universe. When these ultraviolet rays hit hydrogen atoms, they knock the electrons right out, turning neutral hydrogen into its ionized state. You can think of this process as a lightning strike on the atomic scale. These ejected electrons will eventually return to the protons. When they reunite, they release photons of specific wavelengths, which is the light we see. It is this light that makes up the emission spectrum of the Orion Nebula. The most striking pink color, it is a type of light emission called H-alpha. Its wavelength is 656.3 nanometers. Besides that, other colors are also taking part in this storm of light. Oxygen atoms excited twice emit a soft blue-green glow. Sulfur, on the other hand, makes the red deeper and richer. Behind every color, they all contain different elements. Each has different energy levels. When scientists observe these colors through filters, they are not watching a cosmic light show. They are reading the chemical fingerprints of the universe. But this light is not distributed evenly. The closer you get to the T-Tauri cluster, the stronger the ultraviolet radiation, the more intense the electricity, and the brighter the glow. As the distance increases, the radiation weakens, and the gradually returns to a neutral state. As a result, the entire nebula forms a layered structure of light. Hot inside, cold outside. This boundary layer is called the ionization front. It is not a stationary wall. Instead, it moves and erodes. It can even reshape the entire structure of the nebula. Radiation pressure from the stars constantly blows the outer gas outward, pushing the deeper parts. Regions with higher density star formation are revealed. You could say, the light from the Orion Nebula is not just its outer layer, it is also telling the story of the nebula's shape and sculpting its form at the same time. This whole process is not static. It is something we can actually observe within just a few decades. Certain regions of the Orion Nebula have already changed. The Hubble Space Telescope has captured the movement of gas clumps, changes at the ionized edges, and the spread of shock waves. These changes can actually be recorded within a human lifetime. This is extremely rare on a cosmic scale, but do not forget, although this glow is beautiful, it also carries danger. The ultraviolet light that makes the nebula shine at the same time can also destroy the protoplanetary disks around newborn stars, the gas and dust that nurture planets. It could very likely be stripped away directly by this energy, so planetary systems do not even have time to form. That is the most fascinating thing about the Orion Nebula. Its light is the universe burning, but it could also be a signal of destruction for future galaxies. The beauty we see is actually a struggle between life and death. What is even more interesting is this kind of glow is actually hard to see with the naked eye, especially those red emission lines that represent green. The human eye is very insensitive to them. The brilliant colors we see in photos mostly come from long exposures with telescopes and filter stacking. Although these images have been processed, they are not fake. They are translators in the realm of science. They turn light invisible to our eyes into images we can understand. If our eyes were as sensitive as high-performance cameras, what we would see is a stained glass cathedral, lit from within, floating in the universe. And what ignites all this brilliance is a small group of stellar giants hidden in the core of the nebula. They are known as the trapezium cluster. This is the true engine room of the Orion Nebula. If the entire nebula is like a cosmic womb, then the trapezium cluster is its beating heart. Right here, hundreds of young stars are packed closely together. They release light, heat, radiation, and storms. They almost dominate everything. Without them, the Orion Nebula would just be a cold, lifeless cloud of gas. With them, it becomes like a furnace lit from within. This star cluster is called the trapezium because of its 4 brightest stars. See to read. Seen from Earth, they form an irregular quadrilateral. They are all still very young, just a few million years old. By cosmic standards, that is just newborn, but do not think their youth makes them gentle. It is quite the opposite. They are the most violent type in the universe. O-type and B-type stars, their temperatures can exceed 40,000 Kelvin. Each one is a blue-white high-energy bomb. The fiercest among them is called Theta Circumflex 1 Orionis C. A single star like this can supply over 90% of the ultraviolet light in the entire nebula, making the surrounding hydrogen boil. It emits stellar winds at speeds of up to 2,000 kilometers per second. Like bombs, they create shock waves that blast the nebula apart. But the story does not end there. There are more than just these 4 stars in the trapezium cluster. In fact, it contains over 700 young stars. How dense is it? The entire star cluster is only 1.5 light-years wide. That is not even as far as the distance from the Sun to Proxima Centauri, but it is already packed with energetic little suns. This leads to a terrifying phenomenon. They pull on each other. Their orbits become chaotic. One wrong move and a star could get slingshotted out. Some stars have already been kicked out of the nebula and have become runaway stars. They drift all the way to the edge of the nebula. Meanwhile, inside, the circular disks eroded by ultraviolet light also take on unusual shapes. They are torn into teardrop shapes, trailing tails through space, floating like a cloak. What is even more amazing is, after a star forms, its mass starts to stratify. The heavier parts sink toward the center, while the lighter parts are pushed to the outer layers. This causes the brightest and most intense stars to occupy the very center of the cluster, ruling over this chaotic palace like a king. And this palace is still creating new stars. They stir up storms, while compressing the surrounding gas, creating the conditions for the next star to be born. This is the cosmic version of fighting war with war. Stars create more stars, or emerges from chaos. So to understand the Orion Nebula, do not just look at its surface color, shape, and structure. First, look at this star cluster. It is the source of energy, the root of its structure, and the director of all the nebulous drama. But light and heat are not the only miracles here. Within this blazing nebula, there are also some even fainter and more fragile, yet intimately connected to us. These are the protoplanetary disks in the process of forming. They look like ink drops drifting through space, with tails of light trailing from their edges, as if they have been touched by flames. Scientists call these small shadows protoplanetary disks. The English abbreviation is Proplede. These are disks of gas and dust orbiting newborn stars. To put it more simply, they are unborn solar systems. In the Orion Nebula, we are not just guessing how these systems might be born. We are actually witnessing their formation. Thanks to telescopes like Hubble and Webb, high-precision telescopes that can penetrate dust allow us to glimpse the birth of these celestial bodies. Each protoplanetary disk surrounds a young star less than 1 million years old. It is tightly encircled by a ring of material: hydrogen, nitrogen, carbon, silicates, the basic ingredients for life. If all goes well, these dust particles will start to clump together. They go from tiny grains to pebbles, then to mountain-sized embryos, eventually forming complete planetary systems, just like our solar system. But in Orion, this path is almost a disaster. These protoplanetary disks are trying to escape. They are not growing up peacefully in tranquil space, but are at the very heart of a radiation storm. Massive stars like Theta 1c Orionis emit ultraviolet light that heats them up to thousands of degrees and forcibly strips away their gas. This creates tail-like streams of vapor that blow the entire disk apart. This also means that Orion is not just a birthplace. It is also a battlefield. Young planetary systems must race against time to build their planetary embryos before all the dust is completely evaporated. You can think of it as trying to build a house in the middle of a sandstorm, but with a flamethrower blasting fire right at your blueprint. Even so, these protoplanetary disks still persist tenaciously. Some disks farther from the cluster are better preserved, while those closer to the core are eroded beyond recognition. Among them, some are wrapped in curved shock waves, like the scars left in the GA after stellar winds collide with their surroundings, trails left in the flow of GAM. They also resemble the boundary lines of invisible battlefields in the universe. Thanks to the Hubble and James Webb Space Telescopes, we are seeing these protoplanetary disks in detail for the first time, their ring-shaped gaps and concentric structures, and even the paths carved out among the dust. It is as if future planets have already begun secretly marking out their orbits. These signs are very similar to the mature disks we see in images of Tauri and Taurus. The difference is, those are blueprints after stabilization, while Orion is still an active construction site. It is very likely that we were born from such a site as well. Some studies show in the early days of our solar system, it may have also passed near a supernova and even absorbed material released by its explosion. This means we were born out of chaos, rather than a quiet greenhouse. What is even harsher is, not every protoplanetary disk gets the chance to complete its journey. Some disks lose too much mass during their growth. In the end, nothing is born from them. They can only shrink into a failed star, or become a wandering planet with no home, drifting alone in the darkness of the galaxy. So when you look at those bright spots shining in the Orion Nebula, do not think they are just background stars. Some are still holding together, some have already broken apart, some may be giving birth to the next Jupiter. And we are fortunate to stand light years away and witness it all happen. But not all lucky fragments will successfully become stars or planets. In this nursery of the universe, there are also some children who are destined to be different from birth. They are called brown dwarfs. Some people call them failed stars, but that label is actually too hasty, because they are not failures. They have just taken a path no one expected. Their mass is usually less than 8% of the Sun's. This means their core temperature can never get high enough to ignite hydrogen fusion, so they do not shine like real stars. But the way they are born is completely different from planets. These brown dwarfs, like stars, collapse from nebulae, but they are too light to ignite themselves. As a result, they ended up trapped in the grey area between stars and planets. They are too big to be considered planets. In the Orion Nebula, there are many of these identity-lost objects, far more than we ever imagined, thanks to infrared telescopes like Hubble, Spitzer, and James Webb. We have already discovered dozens, or even hundreds of such transitional objects at the edge of the nebula. Some of them are hidden next to protostars, like inconspicuous little siblings. Some drift alone in space, quiet as unnoticed pebbles. Many brown dwarfs are very young, just a few million years old. They are still in their infancy. Even more amazingly, some brown dwarfs also have dust disks, like miniature solar systems. This suggests that even if they never become true stars, they can still nurture planets, and even give birth to their own subsystems. How did they come to be? There are currently two theories. One is that they were born like ordinary stars, but just never grew very large. The other is that they might have originally been part of a larger galaxy, and were later kicked out. It is like in a chaotic struggle for dominance. They were forced off the stage as the losers, and the Orion Nebula happens to provide evidence for both possibilities. We can see some brown dwarfs are still deeply buried in dense gas, like newborn babies, while others have already drifted to the outskirts of the cluster, wandering through space, like children cast out by the universe. Interestingly, some lighter celestial bodies are not even massive enough to qualify as brown dwarfs. They might be only a few times the mass of Jupiter, but they also have dust disks, and could potentially give rise to moons or mini-planets. So what exactly are they? Are they planets? Or sub-brown dwarfs? Or maybe they do not belong to any category at all, or incompletely disrupted these definitions. It made us realize the universe is not a black and white test. It is an experimental field full of grey areas. What is even trickier is that brown dwarfs are too dim. They are completely invisible to the naked eye. They do not emit visible light like stars do. Instead, they give off a faint heat in the infrared spectrum, like a trace of lingering warmth in the night sky. Some brown dwarfs can even erupt with flares, releasing rays, just like real stars. They have active magnetic fields. They are not just lifeless balls of gas. They are alive. They are little things that change and strive to prove their own existence. And now we know that in some star-forming regions, The number of brown dwarfs may actually exceed that of real stars, although they contribute very little light and heat. They hold an important place in the mass ledger. Their gravity affects the orbits of surrounding celestial bodies. Their existence has reshaped the structure of star clusters. They are the true silent majority of the universe. That is why brown dwarfs are important, because they blur the boundaries of the universe, challenging our definitions of what is a star and what is a planet. What is even more intriguing is if they could actually give birth to planets as well. Is it possible that they could also give rise to life? A world without a sun, a faint red dot floating in the darkness. On its orbit, could there also be another kind of civilization hidden there? We still do not know the answer, but every brown dwarf Orion gives us, every trace of infrared glow, is a clue. Maybe not every cloud of Gaia can become a sun, but that does not mean they have nothing at all. Becoming light is not the only thing that matters. Those that are ignited are not the only ones capable of giving off heat, but the birth of a star has never been a gentle story. They do not awaken quietly in peace. Instead, they are violently pulled out of nothingness amidst chaos in the Orion Nebula. This birth ritual is like a cosmic-scale riot. Light, electricity, wind, gravity, and magnetic fields are all churning at once. This is not nurturing. It is more like a tearing apart. Many people think stars slowly grow in the darkness, gradually igniting, but the real Orion is far less poetic than that. It is an interstellar battlefield. Stars are bullets squeezed out by the flow. The Gaia here does not gather gently. Instead, it collides. Tears apart, and spirals at supersonic speeds. Those colorful clouds you see are actually the scene of storms spanning dozens of light years. Each stream of Gaia is like a rocket being launched, racing at hundreds of kilometers per second. They do not pass by each other. Instead, they collide head-on and compress each other. So where does all this chaos come from? The answer is weight. When a cloud of Gaia becomes too heavy and starts to collapse under its own weight, it enters a state of collapse. But this is not a quiet collapse. It is a series of violent explosions. Fragments collide. Clouds twist, spinning rapidly around the core. It is like a jammed blender. Chaos sparks fire, and more extreme still, there are giant stars from the T cluster, adding fuel to the mix. The stellar winds they release, high-speed streams of charged particles, are like jet engines slicing through the mist, tearing open voids along the way. With every passage through, it is like carving a path through the clouds. Each time, it can even spark new explorations. So within this nebula, we'll see sheer zones and swirling clusters intertwined together, like countless irregular placentas. Each one could give birth to a new star. But this chaos does not just belong to the physical world. It also hides another invisible force. Magnetic fields. Powerful magnetic field lines are hidden within the Orion Nebula. They can't be seen with the naked eye, but they are constantly exerting their influence. Sometimes they slow the descent of Gaia, and sometimes they guide the flow in new directions. It is like an invisible cosmic scaffold, but these magnetic fields are not unshakable. When the pressure is great enough, they can also be swept away. They may even make the chaos worse. The result is, stars can form extremely quickly. Some clouds collapse in just 100,000 years. It is almost like a single breath of the universe. But at the same time, more matter is torn apart and burned up, losing its structure forever. This is not a straight line. It is a chaotic chain of creation and destruction, repeating endlessly. In some regions, Gaia barely gathers before it is swept away by shockwaves. In some regions, the air currents collide violently, which actually leads to new discoveries, and scientists observe the movement of these gases with spectroscopy, as if deciphering a silent cosmic dance. They discovered that the Orion Nebula is like a three-dimensional maze. The direction and speed of the Gaia flow are almost completely random. Some rush straight toward us, while others move away. Some swirl and spin, while others shoot straight like arrows. But the more chaotic a place is, the easier it is for new stars to be born, because there, the pressure is most concentrated. Collapse is inevitable. It is like twisting a balloon. When the internal pressure builds up to the limit, the balloon will bulge out somewhere. So stars are not distributed evenly. Instead, they appear in clusters along these chains of pressure. It looks random, but actually hides deep turbulence logic. Understanding this chaos is not just about making a pretty picture. It directly determines the mass density of the star, and even whether a planetary system can form later on. If the disturbance is too strong, the protoplanetary disk may never stabilize and take shape. If the disturbance is too weak, The nebula contracts too slowly, making it even more vulnerable to being destroyed by radiation. The true Goldilocks zone is not just a balance between temperature and density, but also lies in the delicate equilibrium between chaos and order. So when we look at Orion, those seemingly artistic filaments, elegant ripples, are actually the result of a fierce struggle. Stars are not manufactured. They are the victors who have broken free from chaos. Some might ask, Vega, why are the biggest and brightest stars in the Orion Nebula always crowded at the very center? This is not a coincidence. It is actually a phenomenon astronomers call mass segregation. Simply put, the heavier stuff sinks to the center, while the lighter stuff gets pushed to the edges. It is like putting sand and rocks in a jar and shaking it over and over. The heaviest ones always sink to the bottom. But strangely, in the Orion Nebula, this pattern of distribution does not seem to happen over time. Instead, from the very beginning, those massive stars are born right at the core of the cluster. If that is really the case, then the entire rulebook for star formation might have to be rewritten, because this means the birth of massive stars is not a result at all, but rather a script that has been set from the very beginning. Only in the deepest wells of gravity do they have a chance to appear, and in the Orion T-type star cluster there is a star called Theta 1c. It is one of the main characters in this story. Its mass is 40 times that of the Sun, and its energy output is thousands of times greater. A monster star like this does more than just light up its surroundings. It directly rewrites the fate of the surrounding nebula. The ultraviolet radiation, stellar winds, and magnetic field fluctuations it emits can not only blow away gas and heat up the nebula, but also prevent other stars from forming at all. They can even destroy the disk structures where those stars are born. The most ironic thing is, the stars most capable of destroying their environment are actually the ones that form the earliest. What we see today in the Orion Nebula are fragmented clouds, huge ionized structures, and radiation cavities. These are actually traces left by those massive stars taking action first. But here's the question: who decided their positions in the first place, and who gave them priority? One explanation is the gravitational pull between stars arranged everything on its own. This gathering is like a cosmic game of billiards. Heavier stars slowly slide toward the center, while lighter ones are knocked out. But the Orion Nebula has only formed for 1 or 2 million years. There just has not been enough time for them to come together slowly. Another theory emerged. At the very beginning, the protostar at the center grabbed the most gas. It is like getting the best seat at the universe's buffet. It gorged itself and became huge in one go. Those small stars on the edge had limited resources and developed slowly. They could only serve as the background. And what is even more outrageous is the gravity of these central giant stars can also directly affect the orbits of other stars, flinging them far away, or kicking them out of the system, turning them into wandering runaway stars or lonely brown dwarfs. So this kind of mass segregation is far from being a static distribution map. It is a dynamic game of power. The center controls destiny. The edges bear the consequences. Those massive stars concentrated at the center are not quietly shining and burning. Instead, in the most violent way, they are rewriting the fate of the entire nebula. Their lifespans are extremely short. Often, in just a few 100,000 years, they reach their end. They go out with a bang as supernovae, completely detonating their central regions. Sometimes, they even split the entire nebula in two. But before that happens, they have already started affecting everything around them. Their radiation can photoevaporate protoplanetary disks, causing stars are destroyed before they even have a chance to form. Their stellar winds, gravitational disturbances, and feedback mechanisms sculpt the nebula into pillar-like structures, hollow cavities, intense radiation bands, and tangled filaments. The Orion Nebula is not a quiet, diffuse cloud. It is more like a slab of stone carved by radiation, full of curved spires and folds everywhere. It is as if the universe is sculpting a wild canvas with the chisel of light. These towering pillar-like structures are not decorations. They are the scars left behind by radiation carving. Ultraviolet rays from newborn stars are like invisible flames of glass. The low-density gas on the nebula's outer edges is blown away, leaving behind only denser clumps of dust. These clumps are slowly heated, photo-evaporated, and distorted. Eventually, they become what you see through a telescope, glowing filaments and pillars. Some of these pillars reach several light years in height. Their tips glow with ionized light, while their bases are stretched by stellar winds, as if trying to escape some kind of pressure, yet also appearing trapped. struggling within a storm of radiation. At their very tops, you can often see tiny points of light. Those are newborn stars breaking free from their cocoons, emerging at the boundary of radiation and pressure, completing their own birth. This is a cosmic-level elegy. These stars are forming in the very places where they should not exist, forced into existence. You think radiation is a destroyer, but it is also a creator. The density at the top of the compressed pillar actually accelerates the formation of stars, and throughout Orion, there are structures born from such remnants everywhere. Some pillars look like sculptures, magnificent and spectacular. Some look like gaseous serpents, twisting and stretching out. Some are tangled like spider webs throughout the entire cloud, connecting multiple stars. Scientists even suspect these filaments are channels for protostars, the arteries of the interstellar medium, delivering gas to the growing solar embryos. And there is one phenomenon in particular that is the hallmark of the Orion Nebula. It is called the Orion Fingers narrow jets. They shoot outward from the center of the T-Tauri cluster, slicing through the nebula like fingers. They may be the result of stellar mergers or violent collisions, an echo lingering in space after an explosion. They are not stretching out randomly. Almost every one of them is aligned with those stars at the center. It is like grass bowing in the wind. Each strand is responding to the pressure of that light. That is what is most astonishing. The entire structure of the nebula was not formed spontaneously. It was forcibly shaped by the light from the central stars. The images from the Hubble and James Webb telescopes have captured this process in incredible detail. We can see the shadows cast by the pillars, forming delicate filaments. We can see the light from ultraviolet rays and neutral gases. The boundary of ionization we can even see. In some shrinking regions, shock waves frozen in place, like petrified ripples. Every limit, every curl is the result of hundreds of thousands of years of nebular interaction, and most importantly, these structures that seem about to dissipate are actually nurturing new stars. Some gumps are quietly glowing in the infrared spectrum. The density in the middle sections of some pillars is building up, getting ready for the next exploration. Some are fibers connected to protostars, constantly transporting material. So these pillars and fibers in Orion are not abandoned ruins. They are construction sites of the universe. They record the cycle of birth and destruction. They hold clues to the fate of stars and planets, and may even determine whether a new solar system will appear in the night sky in the future. They are not just the background, they are the story itself. If other regions of the Orion Nebula are battlefields where light and gas are chaotically intertwined, then the Orion bar, it is the sharp scar suddenly carved out in the midst of that chaotic battle. It is not as chaotic as other places. Instead, it is an extremely clear, precise front line, as if sliced open. This is no coincidence. It is a cosmic-scale physical phenomenon. An ionization front. In this region, ultraviolet rays from the trapezium cluster. It collided head-on with the cooled molecular gas. The battle froze at that moment, forming a bright boundary. You can think of it as a blade of light suspended in space. On one side is fully ionized, blazing, glowing hydrogen gas. On the other side, it is cold, dense, dark clouds of dust. And in between, that is the Orion bar, only a few 100 billion kilometers wide, yet scorching hot and boiling. In this razor-thin region, ultraviolet light is gradually absorbed, and the atoms are constantly excited and ionized. Everything is glowing. It is like a real-life demonstration of a cross-section of cosmic destruction, perfectly showing how do you sculpt, erode, and reshape a nebula on a scale of several light years. More importantly, the Orion bar is almost directly facing Earth. This allows astronomers to dissect its structure, layer by layer from the front, like slicing a cake, from the fully ionized hydrogen region to the partially ionized warm gas, and finally to the outermost layer of neutral, cold molecules. This structure clearly presents the most important transitional process in the universe before our eyes. It lays it out plainly for us. Moreover, this blade of light is far more complex than we imagined. It is not calm. Instead, it is filled with intense microscopic changes. Within a space only 0.1 light-years wide, hydrogen atoms lose their electrons, and carbon atoms become ionized. Molecular hydrogen breaks apart. Dust is heated until it emits infrared light. Here, almost every particle exists in a kind of critical state. It is as if they are trembling in the flame of light, and the research centered around this blade of light has also revealed the crucial role that dust plays within it. These tiny silicate and carbon particles are like curtains of the universe, absorbing ultraviolet light, protect the molecular gas behind from being completely broken down. Their distribution, density, and structure directly determine whether stars can be born in the shadows. Once the protection fails, the cloud will be stripped away layer by layer, but if the shielding is effective, the embryo of a star can quietly grow behind it. And this boundary is not stationary, it changes over time, slowly advancing inward. Like an extremely slow invasion, layer by layer, it engulfs the core of the nebula. If you could speed up time, the sight would be astonishing. The entire cloud, over hundreds of thousands of years, slowly sliced by the blade of light. Stars form behind the front line, while dust quietly dissipates in the background. Even more surprising is that the shock waves brought by stellar winds sometimes also strike this boundary. These shocks not only compress the gas, sometimes they even trigger new contractions. Behind the blade, new cradles for stars are formed. This boundary, known as the Orion bar, is not just a documentary fragment of destruction, it is also a cosmic assembly line. It is a frontier where birth and destruction overlap. Even more amazingly, on a chemical level, this place is a treasure trove worthy of a laboratory. Carbon monoxide, oxygen atoms, sulfur ions, and even polycyclic aromatic hydrocarbons. Stars all emit their unique spectral fingerprints here. Astronomers can analyze these chemical signals layer by layer to trace how starlight reshapes matter. It is like witnessing, on a molecular level, a cosmic alchemy. Today, astronomical facilities like Hubble, James Webb, and the Very Large Telescope are using their most advanced spectrometers to analyze this boundary of light and darkness layer by layer. They use it to calibrate models, verify formulas, and compare simulations. It is both the most realistic testing ground and the sharpest real cross-section of nebular evolution. This is a boundary, a front line, a window. Here, light has triumphed over darkness, but it has also left scars of light. Yet behind this dazzling front line lies a quieter, deeper power. It does not emit light or explode, yet it is involved in almost every contraction and reformation. It is the magnetic field of Orion, the invisible architect. Within the Orion Nebula, besides the clash of light and gas, there is also an invisible, untouchable, yet omnipresent force, silently shaping all of this. It does not shine. It does not cause explosions. It does not drive storms, but without it, the appearance of this nebula could be completely different. It is the magnetic field, the quietest builder in the universe. Magnetic fields are not as awe-inspiring as black holes, nor are they as dazzling and visible as ultraviolet light. Their existence is crucial to the birth of stars. In Orion, a battlefield filled with flows and gravity, where radiation intertwines, the magnetic field is like a silent referee, sometimes guiding, sometimes blocking, sometimes keeping things in balance, and sometimes gently tipping the situation toward collapse. Although we can't see magnetic fields with the naked eye, scientists have long found ways to peek at them. One way is to observe how light becomes polarized. When starlight passes through dust particles aligned with the magnetic field, the light tilts its head a bit, that is, it becomes polarized. In this way, telescopes are like having X-ray vision, able to map the paths of magnetic fields within the clouds. Sophia, the highly sensitive Alma Ray, and infrared space telescopes, we have already captured the outlines of these invisible forces. They reveal themselves in nebulae as winding, curving magnetic field lines like an invisible jeep, passing through gas, wrapping around clumps, and guiding filaments. Sometimes they flow with the currents, and sometimes they resist, pushing back against gravitational collapse. Magnetic fields are not just quietly posing for us. It also intervenes in the intense motions of the universe. During the contraction of molecular clouds, gravity pulls desperately toward the center, while the magnetic field provides counter-support, like a pole in pole vaulting. Magnetic pressure, this tug-of-war in the dark, determines where stars can be born, and where silence will remain. What is more complicated is that the magnetic field also deals with a tricky problem. Angular momentum, as matter in the nebula contracts. It starts to spin, but if it spins too fast, it acts like a spin dryer, flinging the future star's material outward. The magnetic field works like a braking system, gradually shedding the rotational energy. Otherwise, even planetary systems could not form. And that is not all. The high-speed jets ejected by many protostars may also rely on magnetic fields to clear the way. These jets are not just simple streams of gas, but flows of plasma, guided by twisted magnetic field lines. It is like ribbons woven from light and electricity across the entire nebula. And this is not just rigid theoretical speculation. Observations from Hubble, James Webb, and Alma have already confirmed that in those regions of the Orion Nebula, where stars are being born, or about to collapse. The direction and strength of the magnetic field directly determine whether stars will form there. Even those spectacular structures like the Orion fingers, shapes are also influenced by magnetic fields, and in some seemingly quiet regions, strong magnetic fields act like chains, forcibly holding back air that is about to collapse. Even more astonishing, these magnetic fields may come from the distant past. Some may originate from the death of a previous generation of stars. Some may have existed even before the nebula itself formed. Like an ancestral carving knife, it continues its work among new stars and dust. Do not be fooled by its silence. Every curve of Orion, every fiber, every birth, and every not yet happened, almost all bear its traces. On this battlefield where light and dust clash, the magnetic field is the invisible strategist, also the quietest sculptor, but the side where light wins is far from the end of the story, because, in places where visible light cannot reach, the Orion Nebula hides an even larger, more secretive stage, a world of infrared, concealed behind thick dust. That is where stars are truly born. These brilliant visible lights. It is just the illuminated outer layer of the nebula's surface. Behind them, thick layers of gas and dust shroud the core region like a curtain. The stars forming there are buried deep within dense clouds. They seem silent, but are actually blazing with energy. To uncover all of this, humans must abandon the intuition of the naked eye and use infrared light instead. Just as X-rays penetrate skin, infrared light can penetrate dust and reveal internal structures. When the Spitzer telescope first cast its infrared gaze on Orion, we suddenly saw an entirely new dimension. Protostars that have never appeared in the optical band are now emerging one by one. Some are only a few thousand years old, still accreting gas and spinning out jets, shrouded in dense clouds, emitting almost no visible light. They are the youngest stars in the universe, captured in their moment of birth by infrared light. The James Webb Space Telescope has taken this work even further. It allows us to see not only the stars, but also, for the first time, clearly see the dust surrounding the stars and how it emits its own light. It gives off a faint but real thermal radiation. This glow is different from reflection. Instead, it is a temperature signal released after the dust is heated by the stars. Through these signals, scientists can map the temperature, density, and structure inside a nebula. They can see where it is warm, where it is contracting, and where it is clearing out. Infrared images provide clear, intuitive answers. The infrared view also reveals intricate details of protoplanetary disks. These are disks that orbit around young stars. In infrared, they display gaps and spiral arms, and even possible signs of planet formation. Some are thick, while others are thin. Some have already been eroded by winds from nearby stars. Their outlines incomplete. They are at different stages of evolution, like an interstellar archive of a time series. Even more astonishing, infrared light can also excite specific emission lines from certain molecules, including water and methane, carbon dioxide, as well as organic compounds like polycyclic aromatic hydrocarbons and carbon chains. These building blocks of life glow in the infrared. This allows us to precisely measure their temperature, velocity, and spatial distribution. What we see is no longer just gas, but a table of raw materials for planetary systems and the potential for life. The infrared precision of the James Webb Telescope is so high that scientists can even observe short-term changes in protostars, such as accretion bursts or shifts in shadows. It is like watching a planet factory under construction. Watch how each step assembles the world of the future. And all of this is hidden in the darkest part of the Orion Nebula. Infrared light tells us that stars are not born in dazzling brilliance, but deep within the darkness, silently gestating, igniting, and growing. Worlds that may one day have weather, oceans, or even life, are being born right now in this faint warmth and light. Only with infrared vision can we see all of this. Infrared telescopes have unveiled the deeper secrets of nebulae, but the stars discovered here are not just quietly being born. They may also be igniting the next generation. This is what is known as triggered star formation. It could be the direct result of another star. In Orion, this is not just a theory, it is a fact, especially in the core region known as the trapezium cluster. Some massive stars there emit intense ultraviolet light and stellar winds after they are born, sometimes even with shock waves. These energies constantly bombard the surrounding gas clouds, compressing them more and more densely. When a certain region is compressed tightly enough, gravity takes over, and a new star is born just like that. It's like the first generation of stars ignited the second generation. In the Orion Nebula, We can see traces of this passing of the torch. For example, the distinct edge, the Orion bar, in front is a bright, high-energy region, and behind it are clusters of dense, newborn stars. Their positions are farther back, they are younger. It looks as if they were pushed out by the stars in front. There is a similar structure in the southern region. Scientists have found there are also shock waves there, crashing into denser clouds, and right nearby, a cluster of protostars has just been born. Does not it look like a series of chain reactions, one ring after another? Stars do not all explode at once. Instead, they pass the baton one after another, and this kind of relay can last for millions of years. However, not every trigger like this is successful. If the energy is too low, it can't push the GA. If it is too strong, it could also just blow everything away. Succeed. It has to be just right. The GA must be cold and dense enough, but not too fragile. Scientists use spectra and high-resolution images to determine whether these new stars formed by collapsing on their own or ignited by external forces. In Orion, more and more regions, they show signs of being pressed out. So now we know those strings of stars, those orderly chains of stars, are not naturally lined up. They were sculpted by waves of energy. And when these energy sculptors, that is, those massive stars, reach the end of their lives, a supernova explosion occurs, and perhaps ignites the nebula for one last wave of stars. After that, this place will fall completely silent, the dust will settle, and the story will end. If the pattern in Orion is representative, then we must rethink how stars are formed. They are not born in isolation. Instead, they are ignited by their predecessors, generation after generation, in flames. In this nebula of Orion, we can witness almost the entire cycle of a star's life, from the initial flow of Gaia, to contraction supported by magnetic fields, then to jets igniting the flame of new birth, and finally, one generation of stars triggering the birth of the next. It is like a stellar laboratory built by the universe itself. What we see are data, images, and infrared outlines. But if you look long enough, you will find there is something deeper hidden there as well. A kind of order. And we ourselves, it was also born in a similar kind of cycle. But that nebula is called civilization.